In this video, we're going to be discussing how to implement two-population testing in R. Now, I'm going to skip some of the hand calculation components because it's going to be very similar to what we did in the previous R video, really just using R like a calculator. So if you want to see how to do that, I encourage you to check out that previous video. It's really just going to walk you through some of those hand calculations. What we're going to start doing in this video that we're going to keep doing through the future videos is using R for what I'm going to call real analyses. And what I mean by that is we're going to start reading in data sets and using those data sets to perform calculations just like we normally would if I was, say, getting some data from a client or something like that and asked to analyze it. Now, you'll be able to use these techniques on your homework and any take-home components of exams that we end up doing in this class. So that's going to be where this may play out for you. Now, to start, in this lecture, we're going to be using functions that other people have written. And in R, these are called packages or libraries that we can then load and use so that we don't have to write all of our own code. We can kind of steal from what other people have already done, and as part of the R community, they make it freely available, which is fantastic. So for example, I'm going to install packages and go on and download one called Teaching Demos. So this line, install packages, is the first thing that we have to do if I'm using a new package that I've never used before. Pretty much what I have to do is download it to my computer so that I can then use it later on. Now, once it's downloaded, I never have to run this line again, so I'm going to comment it out. That said, I do have to tell R that for this time that I'm using R, I want to load it. And the way in which I do that is library and then type in this teaching demos. And that's what lets R know, okay, I want to load up this downloaded group of functions so that I can use them today. While you only have to install them one time onto any given computer, so if you move to a new computer, you'll have to redo this install.packages. You have to do the library command every single time you open R for a new time. One of the things that we can do is now we can pull in the functions. So for instance, CIExamp is one of the functions that I can use from the Teaching Demos library. And this just gives me an example of some confidence intervals, 50 different confidence intervals. And I can see how many are don't include the population mean of these 50. So this is just a teaching demonstration confidence interval example. Now, of course, this isn't the point of what we're doing today. The point of this little section is to discuss how to install and load libraries. And again, the fact that you're going to have to install, which in R's terms really just means download, these libraries once per computer, but you're going to have to load the library every single time you open R if you're using that library for your code. So we will be using that later on in today's R session. The second different thing that we're going to talk about today, and I'm going to go on and clear out that plot and do Control L to kind of wipe all the stuff on the right there, because again, we're kind of done with the teaching demos for now. But the second thing that we're going to be talking about is how we organize data. Now in statistics and when we're dealing with data, we often have tables of data that we're using for calculation. Typically, I don't have to hand type anything. People give me data in like Excel. Sometimes they give me data as a CSV file or something like that. So sometimes I have to manually type it, but often it's built into a different file. So today we are going to talk about how do we read in data from like a CSV file or from an Excel file. Now, part of the issue with this and with everything that we're going to work on with this data format is that when data is put into a table, there's a couple of different ways that it can be written into a table. So we might have a wide format or a long format depending on how we want to construct it. So I'm going to go on and type in a group of values. So this is some GPAs for males, and then I'll do GPAs for females. This has been an example we may have been using in class. So this is my males. Then I'm going to go on and type in a vector of female GPAs. Awesome. So I've got these two written out. Now I can make my matrix in R by using what we call a data frame. So these individual values we mentioned, or excuse me, these lists of numbers we mentioned at the end of our last R video are called vectors. And if I type M or F, you're going to see that all three of these numbers come together and that they're grouped together in that way. For a data frame is going to combine all of this into a single, kind of like a matrix or an Excel. You can think about an Excel spreadsheet if you want a little bit. So I'm going to type data.frame, and then I'm going to put in the values that I want to be in my data frame, in this case M and F. When I look at this DAT, you're going to see that I've got these row descriptions, 1, 2, and 3, just saying they're just the numbers of what row it is. And then my columns are called M and F, and then within each of the columns I have these particular values. Now once I have data organized in this way, one of the reasons I really like data frames in R is I can easily pull out just the male column or just the female column from this DAT data frame. So from a data frame, if I want to pull a particular column, I'm going to type in the name of the data frame, in this case DAT, and then use a $, and then put in whichever column I want. So if I want the male column, I'm going to do DAT $M. If I want the female column, I'm going to do DAT $F. And that way I can really quickly calculate, let's say, the mean for the males, mean DAT $M, and the mean for the females, mean DAT $F. So this is an example of wide data, and what I mean by wide data is that I have a group of independent values. So that is, they're not matched samples. These are just 3 random males and 3 random females. They're not connected, and I had them in vectors, and then I just put them side by side in this matrix or data frame format. So this is what we would call a wide format of the data, where the columns actually represent a variable. The columns are the sex, male and female. Now another way in which I could do that is I could have a column for sex. So a column where I list male, female, male, female, male, female going down instead of across. And that's going to be called a long format data. So what would this then look like? Well, if I have male, female going down, I'm going to need this outcome information to be written somewhere. So I'm going to have another column called GPA, which just has all of this outcome. So GPA is going to just be, I'll put my males first and then my females second. So GPA is just a list of all of the different GPAs. And then I'm going to have a sex column, which is going to have male, 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 because the first 3 observations are males, and then female, 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 because the next 3 observations are just female. And then when I put them together, I'll call this DAT long. I'll have sex and then GPA. And if I look at this, you'll see that how this comes out is that the first person is a male and had a GPA of 2.58. The second person is a male with a GPA of 3.48. The third person is a male with a GPA of 3.95. The fourth person is a female with a GPA of 3.58. So this is just 2 different ways to organize the information. Sometimes the information comes in either way. Typically long is a little easier to deal with, but we'll demonstrate how we can work with both of these for our testing later on in this video. All right, last thing I told you is we'll talk about importing from Excel and a CSV file. So I'm going to talk about both of these together. First of all, I'm going to talk about writing to a CSV file. So if I want to take, let's say I want to take my DAT long and write it out as a CSV file. CSV stands for comma separated values, CSV. Then I use the write.csv command that's built right into R. I don't have to do anything special for that. I give it the data set that I want to write, and then the file name that I want it to be called. I'll just call this longdata.csv. Now this longdata.csv file, when I write it, is going to go into a file called longdata.csv. And the .csv is really important because if you don't put the .csv, your computer isn't going to know what kind of file it is. So longdata.csv now exists. And if I want to read, or that is import data from a CSV file, I can use the read.csv command. And this time I just tell it what file to look for, longdata.csv. And I can see that it reads in. Now, one interesting thing that you're seeing is happening here is it reads in the sex and the GPA, but something weird is going on in that first column. And the best way we can explore this is to actually open that CSV file in Excel. So I went ahead and pulled up where I'm working. This is the directory I'm working in. And I can go on and open up this CSV file in Excel. And what you'll see is that I have, instead of 2 columns that I was expecting, the sex and GPA like it demonstrates in R, there's a third column indicating those row designations. Now I can keep that from happening. I'm going to go on and X out of this. If I do write CSV, I can give it one more argument, and that is set my row names equal to false. And that's going to keep it from reading in those row names. So now when I open it again, it's not going to have those row designations. Now if you actually assign row names, we may talk about that later in this video, then you want to keep that row names equal to true. But if you don't have row names, if it's just numbers, sometimes that gets a little too confusing, and maybe you want that set to false. Now when I read in this CSV, this is reading in just like I expected it to for dat_long. And then if I just read it in, that's not good enough. Like that reads it and it prints it, but it doesn't actually save it as a variable. So if I want to save it as a variable, I'd have to call it like maybe dat_long CSV. And now it's a variable that I can call later on in my code if I want to use it. All right, so to import from Excel, which we said we were doing, I actually need an Excel file. Now we can write to Excel if we want to in R, but it's a little tricky. In fact, what I'm going to do instead is just log into my CSV file and go to File, Save As, and I'm just going to save this as an Excel workbook instead of a CSV file, so that I have an Excel file called longdata.xlsx that I can import. Now I'm going to need a package, so install.packages, and the package that I'm going to need to read in an Excel file is cleverly called readxl, all lowercase. Now it's important that when you install packages, you wrap the package name in quotes so that R knows that this is the name of the package. If you don't do that, you'll get an error, and if you get a cryptic error when you run install packages, just make sure that the package name is in quotes. Again, after I run that, I can comment that out because I only need to run it one time per computer. But I need to do this library command every time on the computer every time I reopen R. So I comment out the install packages, but I don't comment out the library stuff because I'm going to have to redo it every time. So once I have read Excel, I'm going to use the read_Excel command. Now what's weird is in the write CSV we had file, giving it the file path. In read Excel, it asks for path to give it the file path. I'm going to give it longdata.csv. Oh, excuse me. There I've got an error. So error, can't figure out if the input is XLS or XLSX, so that's the old version of Excel or the new version of Excel. That's because I'm telling it to read in the CSV, not the XLSX file that I just made. Once I give it the proper file name with the XLSX file, then we can see that it reads in. It reads in as a tibble, which is pretty much a fancy data frame. We won't really work into that. here. And again, you'll note that when it reads in like this, it just prints it right out. That doesn't actually save it. So if I want to save it to be used later, all right, maybe dat long Excel, and then read Excel. And then if I want to use it later, I can using the variable dat long Excel. All right, so this is reading and dealing with data in R. And why this is important is as we start using these R functions for running things like a z-test or a t-test, typically we're going to do these not with data that we type in by hand. I mean, we will for like a homework problem or something, but if you're working on a project, you're going to be doing this with real world data. You don't want to be working on something like that's very limited in this way. Oftentimes in real world data, people use Excel sheets. That's probably the most used thing that I get from clients is Excel sheets. So you're going to want to be able to handle that within your code. All right, so let's jump into this. And again, we talked about single sample tests, but now we're going to be talking about how to use the built-in functions in R with our data sets to be running these. Now I'm going to use for the z-test install packages capital BSDA, and remember R is case sensitive, so you want to make sure that you use the capital letters if you are trying to load this up. All right, so now that that's done, I'm going to comment that out so I don't accidentally run it again. It's not the worst thing in the world if you accidentally run it again. In fact, you just saw R give me a warning saying, hey, you already have this. You don't need to run it again if you don't want to. So again, it's not the worst thing in the world if you run it. It just takes a little bit more time because it re-downloads it from online. So it's not needed. In this particular case, I actually have two z-tests that I can run. They're both called z.test. One is from Teaching Demos and one is from BSDA. When this happens, I can specify with R which one I want to run by giving the package name and then a colon, and then writing the function that I want from that package. So what this tells R is look in this particular package and then find, the colon says look for this z-test, and this is the z-test I want to run. Now for the first time I run a function, I might do a question mark and then look up the function and see how it works. So for a single sample z-test, I have x, which is a numeric vector, and then remember I compare to a single number mu for a single sample test, and then I'm going to need to give it the population standard deviation sigma. You can look up more information and examples on that if you want to. In this case, I'm going to look at the males from the DAT data frame. I'm going to compare that GPA, the male GPAs, to a mean of 2.5. That's my null hypothesized value. And then I'm going to assume that the population standard deviation is 1. So here, it's important to realize that this is the population standard deviation, not the population variance. So if you're confused about that, make sure that you're finding the population standard deviation. That's what R is looking for with this sigma value. Running this test, we can see it's a one sample z-test. I have a test statistic, I have a p-value. Now what's interesting and nice about R is R tells me that my my alternative hypothesis, not my null hypothesis, is a not equal to alternative hypothesis. So this is running a two-tailed test. If I want to run a one-tailed test, and two-tailed is what R runs by default. If I want to run a one-tailed test, I have to give R the alternative hypothesis. So this could be greater than. So if I think my mean value is greater than the null hypothesized value of 2.5, the alternative is greater. And you'll see that the p-value changes because R is automatically doing that doubling of the p-value for us. I can also do less than if I was hypothesizing that my that my data is less than the mu of 2.5. And given that my sample mean GPA for the males is 3.33, there is very, very little evidence to suggest that a mean GPA of 3.33 at the population level is smaller than a GPA of 2.5. So very little evidence to suggest that. Here we're borderline. If our alpha was 0.1, we would be significant. If it was 0.05, we would not be significant. And for the two-tailed test, we would not be significant at either of those. So that's how we would run all three of those. So we can also run a t-test in the same way. So note that for a t-test for a single sample, I still need to give it the data that I'm using, that I want to use. So in this case, that's the males. And I also need to give it the comparison value, but I don't need to give it the population standard deviation, because with a t-test, I'm not assuming that I know that. In this case, looking, you can see that the mean estimate is the same, but what's changed is the test statistic. Instead of a z, now I have a t. Notice it gives me a degrees of freedom, and you'll also see that the p-value has changed from my original test. So this is my original two-tailed test. Down here you can see the p-value is slightly bigger for the t-test, and the reason it's slightly bigger is because we have a little bit less information. We don't know the population standard deviation. Note that the alternative hypothesis is also listed in the t-test, and we can see that this is the non-directional. You can make it directional by adding these alternative lines into the t-test. So I'll just do this for 1. In this case, it would make the most sense, or be the most likely that the alternative somebody would be interested in would be if the mean GPA was greater than a GPA of 2.5. All right, so let's jump into the two-sample test. So that was the one-sample test for T and Z. So I'm going to again specify that I want to use the z-test function, not from our package earlier, but from the BSDA package. And now, instead of just giving it a single sample, I'm going to give it the males as my first sample and the females as my second sample. Now for this, I still have to set the population standard deviation for the first group and the population standard deviation for the second group. I'm going to assume that both of these are 1. Note that what this is doing is taking the males minus the females. So if I want to look at alternatives of greater than or less than, by default it's not equal to, then I need to be really, really careful that I'm putting the right groups in the right order. In this case, again, it's males minus females that's coming up with the test statistic. Same way I can run the t-test. I just give it the males and the females, and I don't have to do anything else, because again, by default it's going to compare them and see if they're different than 0, if the difference between these groups is 0 or not statistically significantly. Now this is the way in which we deal with this with wide data, but there are some functions which allow you this is the way we deal with this when we're using these specific vectors, but there are some functions that allow you to just give it the column names and then later specify what data set you're using. So I can just give it M and F and then tell it that the data set that I'm using is the DAT data frame, and that's pretty handy. The z-test I don't think functions like that, but the t-test and several of the other functions we'll use through class do. This is a little bit easier because I don't have to specify that the male column came from the DAT data frame and the female column came from the DAT data frame whenever I call them each. I only have to specify once per line of code that I'm using the DAT data frame for all that. It makes it a little bit easier. The other thing is when I'm using long data, I can write this in a little bit of a different way because I don't have a male column and a female column with long data. What I have is GPA which has been broken down by sex. So if I look at dat long, so that you can remember what that looks like, I have sex and GPA, and what I'm trying to compare is I want to break down this GPA by sex and see if broken down by sex there's differences between the sexes. So I take my outcome and I put that first, and then I put a little squiggle to say I want to break down this variable on the left, my outcome GPA, by sex. And then again, I'm going to say the data is dat. Note that what you'll see here is the same p-value as what we were getting earlier. You'll actually see that the t-value is negative instead of positive. This is indicating that the order has been switched around. I believe R by default uses alphabetical order, so it puts it in M, or it puts F before M when it breaks it down on its own. It very nicely gives you the mean values of each of the groups too, so that you can clearly see the females have a slightly lower GPA, but because P is greater than alpha, this difference is not statistically significant for this particular data. All right, so this has been how we break down the mean values. Let's look at the matched samples. So in the matched samples, I'm going to do the pre and post test on technical aptitude. And I'm going to say I have 3 people, Antonio, Kelly, and Tori. So I'm just going to say my people, and I'm just going to write down their names because I'll label the rows after them later. Antonio, Kelly, and Tori are my 3 people. I use random number generators for all of these numbers, by the way, that I get. Incidentally, the people's name in R, there's a random name generator that you can use, and that's where these people's names came from, as the random name generator. So for the pretest, and this is really important when I'm looking at matched sample data, it's important to put them in the proper order. So if I'm going to use Antonio, then Kelly, then Tori, and you know, if you were doing states of deliveries, we had a problem like that in our notes too. You would just want to make sure you list out all the states here, and then put the pre and the I think it was UPX and DeliverX or something like that. You would put those times in the same order as the names. So in this case, I want to make sure my pre values, my post values, and the people's names are all in the exact same order. So in this case, I want to make sure I have Antonio's pre-value first, that I have Kelly's pre-value second, and then I have Tori's pre-value third. And then post-value, again, I want Antonio's post-value first, Kelly's post-value second, and Tori's post-value third. And again, it's really important that you get all of these lined up. Now I'm going to go on and put these in a data frame, so I'll call it match dat. And I'm going to do pre and post here because these are my data values. But if I look at match dat, it doesn't give me the names of the people. Now that doesn't particularly matter. You know, person 1, person 2, person 3 is fine. But if you wanted to add the names of the people for each of the rows, there's the row names argument that you can add. So row names for match dat. Let's say I wanted to make those my people's names. And then when I look at match dat, I can more clearly see, okay, these are Antonio's pre and post scores, these are Kelly's pre and post scores, and these are Tori's pre and post scores. So once I have my data set up like this, it's actually pretty easy to do a t-test on this. So when I do t-test, I'll just use the t.test command like I did before, and I'm going to give it my 2 vectors like I did before. So I'll have match dat pre, and then match dat post. And then the thing that I'm going to do to change this from being a regular t-test is I'm just going to let R know that this is a matched samples. Now R doesn't use the term matched, it uses the term paired. So I'm going to say paired equals true to let R know that each of these values are paired up. And when I plug that in, it runs this paired t-test. And again, by default, the alternative hypothesis that it's doing is a not equal to hypothesis. You can set greater than or less than if you want to. Now I should note that again, the direction of difference is important. So in this case, I have pre minus post, and that's negative. What does pre minus post being negative mean? Well, you can write this out, and I encourage you to do this. Honestly, it takes a lot of time to get the hang of this, but pre minus post being negative means that pre is smaller than post. So again, kind of write that out, write in a couple like numbers for pre and post, just make up a few and say, okay, what's a bigger number pre than post? What's a smaller number pre than post? But if it really gets confusing, you can always just really quickly calculate the mean of matchstat pre and then the mean of matchstat post so that you can figure out, okay, the mean of the pre is 51, the mean of the post is 55. So this is a statistically significant change using a two-tailed test, and alpha equals 0.05. P is less than alpha, so we have enough evidence to determine that pre and post are different. Well, which one is bigger? Well, post is bigger. How do I know? Well, I went and found the mean of the pre, the mean of the post, and I can see that the mean of the post is bigger. Why would I do this? Again, because sometimes this mean of the difference doesn't really tell me anything. Negative 4.3, it can be confusing to know which direction that goes. And how it is it's the first number minus the second number, but again, that's not necessarily any more helpful. So sometimes it's nice to just calculate the mean of each of the groups that I'm looking at and look at those means. All right, for our tests of proportions, we have a couple of different ways that we can break this down. For the one sample test for exact, so I'll write exact one sample, we can break this down in the binom test. And I give it three things. I give it an x, I give it an n, and I give it a p. So x is the number of successes. I think in our notes we had one with 120 successes. N is my total sample size. We'll just say 220. And then p is the null hypothesized probability value that I'm comparing. Let's say I'm comparing to 0.5. And if I run this, this is going to give me a test. Notice it gives me a 95% confidence interval 2. It gives me a probability of success is not equal to 0.5. So again, the default test is not equal to, and I can go and pull these alternatives and add them down here if I wanted to change that. Note that for the confidence intervals, a lot of these are giving confidence intervals. This is fantastic. That means that you can go on and calculate your confidence intervals via these if you wanted to. But sometimes you don't want a 95% confidence interval. So how do I deal with this if I don't want a 95% confidence interval? Let's say I wanted a 99% confidence interval. Well, I can use this confidence level argument and say I want a 99% confidence level. I could write my confidence level equal to 0.99, and you'll see that if I run that line, now instead of having a 95% confidence interval, I've gotten a 99% confidence interval. Pretty handy, pretty quick, pretty easy. Now, if I'm okay with using the normal approximation, there's another test that I can run called the prop test, and this is usually fine if I have a big enough sample size. So let's say I have 120, just like before, n equals 220, and p equals 0.5. I can run this test. I get a very similar confidence interval to what I had before with my 95% confidence interval to within rounding error. So this is going to give us very, very close numbers. The binom test is exact. The prop test is a estimate that I use based on the normal distribution, the normal approximation of the binomial. Why would I ever use this? It's a good question. The reason I'd use this is because sometimes the exact test is just too strenuous to calculate. It takes too many computing resources, and it's just not worth it. The other reason I use this is both of these work for the one sample, but if I want to do a two sample case, I have to use the prop test. What I end up doing is I end up writing the number of successes for both my first and my second sample. So in our notes, we had like a campaign marketing, and then we had a brand awareness before and after the marketing. And before, I had 60 people who were aware. Afterwards, I had 120 people who were aware of my brand. And then after the number of successes, I type in the number of people I actually talked to. So in the first time, I talked to 150 people. And in the second time, I talked to 250 people. So the first vector is my number of individuals who recognize the brand. The second one is how many people I ended up talking to. And once I create both of these vectors, I can plug these into prop test. So prop.test. And then instead of x equals a single number, my number of successes, now I have a vector of successes that I type in. And instead of my sample size being a single number, now I have multiple sample sizes for my two trials. This is how I would then compare my proportion 1 and proportion 2 to each other. Again, note that the order is important. So in this case, I have my before the campaign and after the campaign, and this is calculating the interval for before the campaign minus after the campaign. So this is saying, is my number before the campaign higher? It's looking at the amount higher. So negative would mean that it's lower, not higher at all. If I wanted to switch this around, I could switch the order of the numbers, but I'd have to do it both in the number of successes vector and in the number of trials vector, because I want to keep the numbers aligned with one another. So 120 and 250 should either both be first or both be second, but you shouldn't jumble them all up, because then R will get confused. All right, we're going to close this out with the test of variance. Now, the test of variance that we talked about, again, depending on what you covered in your previous statistics courses, could be a little bit different than things you've seen before. So the first thing we're going to talk about is the chi-square distribution in R. So I can set my probability just like before with the Q norm and QT, Q chi-squared. I set a probability, and remember chi-squared has a degrees of freedom, so degrees of freedom equal to 9. And this gives me the area below. Now it's important to realize, because this is a little different from our notes, that Q chi-squared defaults to the area below. Remember, we can change that by setting lower.tail equal to false, and this gives me the area above. So this is asking, this first one is asking what chi-squared value has 97.5% of the area below. This second chi-squared value is asking what, or the second chi-squared is asking what chi-squared value has an area of 97.5% of the area above, with a lower tail equal false. If I wanted to find a p-value for a test statistic, I'd give it my test statistic. So we'll say this is 12.6. I think this is what we found in the notes. And then I do the p chi-squared just like I did the p norm and the pt. Now my first argument's just going to be that test statistic. Then I'm going to tell it how many degrees of freedom I have. And then I'm going to determine if it's an upper or a lower tail test. Now if it's a lower tail test, I can type lower.tail equals true, or just leave it because that's the default. But if it's an upper tail test, I'm going to type lower tail equals false. And I need to type in my TS. So this would be the p-value for an upper tailed test. Now remember, if it's a two-tailed test, I would kind of run the lower tail equals true and the lower tail equals false. I would take the smallest number and then multiply it by 2, and that's how I run my p-value for a two-tailed test. So you can look at the previous video or kind of revisit what I just mentioned and think about it a little bit in the context of what we talked about in class, but that's how we would end up running our test. So this is how to do these by hand, but doing the test in R, we're going to get yet another package. So install.packages, we're going to grab env stats with a capital E and a capital S. and then I'm going to grab, so once that's installed, again, I can go in and comment that out because I only have to do that once per computer. And then I'm going to run that library command, and that's what tells R to kind of load up that so that I can use it right now. And I have to do that every time I load or reopen R. So in our particular case, I'm going to cheat a little bit. You're welcome to pause and type in the data. I've already typed all this in, so I'm going to cheat and copy and paste here. So again, pause if you need to, or you can look back in the notes to type in the temp data from what we had in the notes. The command that we're going to use is var test with a capital T, and I'm going to give it my data set. In this case, it was a temperature data set. I'm going to give it the sigma squared. This is the variance that I'm seeking to compare to. So remember, this is a one sample test. I'm comparing to a fixed value. In this problem, it was 0.5. And then in this particular problem in our notes, we were looking to see if my variance in this temperature was greater than 0.5. So it was a one-tailed test in the greater direction. You'll see that I have my test statistic. This matches what we calculated by hand in our notes, the degrees of freedom and the p-value. You'll also see my estimate of the sample variance, which I can do just by typing var temp. And don't forget that the standard deviation is SD temp if you wanted to find those. So variance and standard deviation for the sample are pretty easy to find in R. So remember, for the variance of two samples, we had a whole new distribution, the F distribution. So just like we had before with Q chi-squared, to find the table values for an F, we use QF. So let's say I wanted to find 5% in the upper tail. So actually, I'm going to do P equals 0.05. So 5%. My degrees of freedom, remember I have two, so in R it's called df1 and df2 for my two sets of degrees of freedom. So my degrees of freedom for the numerator, or the first degree of freedom, is 9. My degrees of freedom for the denominator, or the second degrees of freedom, is also 9. And then if I want to find 5% in the upper tail, I'm going to write lower tail equals false, and this is going to find what F value gives me 5% of the error in the upper tail. Now, in the same way that I could find the p-value with the chi-squared, I just calculate my test statistic. I think in our notes we had a test statistic of 2.53. And then I type in PF, and my first argument's my test statistic, and that's how I go on and calculate the p-value. Now again, for the F, I have 2 degrees of freedom, and I need to enter them both. df1 is 9, df2 is also 9, and this just comes from our notes. And as I mentioned, there's 2 ways to do this. I'm going to run it with lower.tail equals true, and then I'm going to run it with lower tail equals false, and I'm going to see which of these 2 numbers is smaller. So in this case, the second number is smaller, so this is the one I'm going to go with. This was a two-tailed test. And so to find the p-value for a two-tailed test, I'm going to take the smaller one, that's with the lower tail equals false, and I'm going to multiply it by 2. How do I know this is a two-tailed test? This just comes from our notes. From our notes, as we wrote the Nolan alternative hypothesis, we saw that this was a two-tailed test. In those notes, how do we tell if it's a one or two-tailed test? How do we tell how to write the hypotheses? Well, I look at the problem. If it's a greater than or a less than problem, it's a single-tailed test. If it's just a generic difference and we don't specify a direction, then it's going to be a two-tailed test, one of those not equal signs in the alternative hypothesis. And that's what lets me know I need to do this, to look at both the lower tail equals true, the lower tail equals false, and then find the smaller number and multiply that smaller number by 2. That's what's going to give me my p-value in a two-tailed test. All right, so how do I actually run the test in R? So for the test in R, I don't have to use a new package for this one. I've already loaded everything that I need. What I do need to do, though, is write the temperature for the second samples. So again, I'm going to cheat here and copy. I've already got it typed in. You're welcome to pause the video and type this in if you'd like, or you can go onto your notes and grab it from there, whatever's more convenient for you. Recall that when I did this in my notes, I said that I have to put the one with the higher variance on top. So I'm going to go on and check the variances of these two. I'm going to have the variance of temp, which is the first temperature data set, and the variance of temp 2, which is the second temperature data set. I see the variance of temp 2 is higher. So when I use this next command for comparing my two variances, I'm going to put temp 2 first, or on top, because that's what we said to do in our notes. So running the test, I am going to use the var.test command. And again, I'm going to put temp 2 first because it had the higher variance, and we said the higher variance has to go first or on top. And then I'm going to put temp, and this is going to run my comparison. Looking at this, I see I have my F statistic, my test statistic, my numerator degrees of freedom, that DF1, my denominator degrees of freedom, and my p-value. You'll see this test statistic, 2.525, is within rounding error of the test statistic I found in my notes, and the p-value, 0.1838, is within rounding error of the p-value that we calculated using R. This has been a discussion of how we run two-population testing for the mean, proportion, matched samples, and variances in R. I apologize for the length of this video. This should be the only video we're doing today. So I'm sorry about that, but hopefully this was helpful. As always, please feel free to reach out with any questions.